HVAC 360, episode number 49, Duct Leakage Testing. Welcome back, everybody, to another episode of HVAC 360. I'm your host, Matt Nelson. Today we're going to be talking with Mark Terzigni of SMACNA, and we're going to be talking about duct leakage testing. A little bit about, ductwork construction, a little bit about the testing itself, but, it's really, I guess, important to understand and realize the things that go into duct leakage testing, because you spend all the time designing, you spend all that time constructing. You want to make sure that you get it right, and again, the only way to really prove out that your design and installation is correct is to do some verification with some testing. So a lot of people might be a little bit fuzzy about what it looks like, and how you do it, how you specify it even. So I just wanted to kind of go over some of the basics that a lot of people may not already know. So I think I'm going to rely on my friend Mark to talk about this, and we'll see what Mark has to say. So let's cut to the tape. All right, this week we're talking to Mark Terzigni. Mark is a project manager at SMACNA for their technical resources department. How are you doing today, Mark?
I'm doing fine, Matt. How are you?
Good. Hey, why don't you tell me a little bit about your background as far as, how you get into the business and, a few things like that.
Okay. Well, I guess the relevant portion is I attended a small Midwestern university called The Ohio State University. Graduated from there with a Bachelor's of Science in Mechanical Engineering. And when I was getting close to graduating, I was trying to decide, like most soon-to-be graduates, what was I going to do. And for whatever reason, I liked the construction industry, so I started to focus on that end, and I got a job with, they claim, I guess, the largest manufacturer of ductwork in the United States, a company called McGill Airflow.
Okay.
Anyway, started there. I was a sales engineer, so I would work with consulting engineers, help them. A lot of times I get called in to say, hey, take a look at our design and what can we do to truly value engineer it. A lot of times value engineering is just taking stuff out. We would go through and say, you can actually achieve good performance and do it with spending less money by doing the following. Most of the time it had to do with just evaluating the types of fittings that they were using. I also got a little bit of a background there in doing duct acoustics. So we would go out and do acoustics for duct systems. And, of course, they also sell leakage testing equipment. So I learned about that, the background of that, and went out and taught many contractors, typically for that application, how to set one of those up and do the test and read the charts and et cetera. Anyways, from there, an opening came up at SMACNA. They had somebody retiring, and like most jobs, from somebody I knew that knew somebody knew that the position was available, asked me if I was interested, and sent in a resume, and came on board at SMACNA about 5 years ago. And now I oversee the development of a number of standards, including duct construction. Our topic today is on air leakage of ducts, and we just finished the second edition of that manual. Just came out a little bit ago. Was the lead on that one. Also did a couple of apps for SMACNA, one of which is a leakage calculator, which I'll talk about when we get to that here today. And that's basically it. Also a member of ASHRAE, chair currently of TC 5.2, which is duct design, and a slew of other associations that are related to the industry.
Now, somebody not familiar with all the acronyms, SMACNA stands for?
SMACNA is the Sheet Metal and Air Conditioning Contractors National Association. That's what that stands for. And basically what we do as an association, any trade association, that's interesting too. Never knew what a trade association really was until I came to work at SMACNA, but every industry has at least one, if not more than one. And basically they advocate for their industry. we develop standards in our case. We're also what's called an SDO, or a standards developing organization. So we develop standards that are relevant to the industry. We also develop guidelines and other documents. We advocate on behalf of sheet metal contractors when it comes to things like code hearings and things of that nature. And we even maintain an office on Capitol Hill to help, I'll say, direct legislation to benefit our industry, which is the sheet metal and air conditioning industry. And just one other little side branch, a lot of folks relate us to air conditioning because our biggest selling standard is duct construction, but we also do architectural sheet metal, so roofing, gutters, things of that nature. We also have a standard for that, or actually technically that's a guideline. But we have a document for that for the architects to use.
Now, is SMACNA sort of a U.S.-based or a U.S.-focused organization?
Well, we do have, we actually have a large membership in Canada. We've recently been growing quite a bit in Canada, as many people will realize their construction economy is a little different than ours right now. It's doing well. So we've got a number of members in the Canadian area, but we also have chapters in Brazil. We have a chapter in Australia. So we are, I guess, technically international, but yes, the majority of our focus, the vast majority of our membership is within North America, I would say. So we have a pretty active Canadian and United States base of members.
Now, I guess let's talk a little bit about duct leakage, the topic that we're covering. You have duct leakage, you have equipment leakage. Can you kind of go over the difference between the two and the importance of them?
Sure. Well, first let's talk about duct leakage, because that phrase is quite often misused, and I mean a lot. Because a lot of times you'll see, particularly research projects, and they'll say duct leakage accounts for X% of system losses. And as a guy who represents the folks who typically manufacture and install duct, we get a little upset by that, because our research and other research actually shows that it's not just the duct, okay? And this is where we get into the difference. People say duct leakage, but what they really mean is what we would call system leakage, meaning it comes out of the system somewhere. But the system leakage is really divided into the duct itself, and then you have equipment leakage, and you even have what I would call accessory leakage. Okay, things like fire dampers and things like that aren't really equipment, aren't really duct work. That's kind of the accessory. And those things all total up and give you system leakage. Equipment leakage, of course, as the name would imply, is the leakage from various pieces of equipment, like an air handler, a VAV box, things of that nature. Okay, but again, the term duct leakage is almost always used in place of the word system leakage, and that's probably because we've had a standard that addressed duct leakage for a very long time. Our first standard on that was published as a separate document has been around since '85. But even before that, it used to be incorporated in our duct construction standards before that as a method of test. But there is a big difference now. For instance, ASHRAE 90.1 is an energy standard. We made a really big issue about saying, look, guys, we've gotten the duct to be pretty tight. Our research shows that it's pretty tight. It's sure it's not zero, and can we get it to zero? The answer is yes, it can be zero, but there's a certain cost involved in that. And what we're trying to do is get the industry aware of there's other lower hanging fruit right now. Let's bring the other components that make up a system, a distribution system for air, up to the standards of the duct, let's say, and then we can go back and say, okay, now let's go back and get the duct tighter if we can. But everything has, a practical limit. It's all related to cost. The fact of the matter is, you can order or specify, if you want, zero leakage duct, but it's going to be expensive. It's typically fully welded and bubble tested, and it's just done to an extreme that is not generally acceptable, or even it's acceptable, I guess, and it's just not practical for your typical HVAC application.
So now, I guess, what sort of standards? You've mentioned a couple of standards that SMACNA has. I mean, are these pretty much the de facto standards that govern the industry? Okay.
Well, yes and no. And SMACNA, as a standards developer, We are also an ANSI standards developer, and I guess just to cover the difference between an ANSI standard and a non-ANSI standard. ANSI, to simplify or give you a short definition of that, would be it's consensus-based, meaning that when we get a standard and it has an ANSI stamp on it, that means we've opened it up for anybody, and I literally mean anybody in the world can post a comment, and it has to be addressed, and we have to go through a process. And then it goes out to what's called a canvas body, which is made up of industry professionals. But again, anybody can request to be on a various canvas body, and we have to make that group happy, before we can get an ANSI stamp and put the standard out there. So we are the only freestanding, if you want to call it that, ANSI standard that addresses duct leakage. It covers how to do the test, the pass-fail criteria, everything like that. Now, H3 90.1, which is also an ANSI standard, but it references our standard, the SMACNA standard, in there. It does have leakage criteria, but it's based on the same principles and methodology that you would find in the SMACNA standard. So there are multiple standards that have it. There is another industry standard. It is not an ANSI document. It's not even really publicly reviewed, but I do see it referenced from time to time. It's from another associate. They're not a trade association, but they do have a standard that addresses leakage, and they approach it in terms of percent, which is something that we don't advocate, and there's good reason for that. So, but for the most part, yes, the standard that is referenced in any building codes, mechanical codes, 90.1 would be SMACNA's HVAC air duct leakage standard. And since we just came out with a second edition, it may refer to either the first or the second edition. The only real difference between the two is that we actually lowered the leakage classes. So we reduced the amount of acceptable leakage from the first edition to the second edition by roughly 30%. And then there's also a new chapter in that standard, the very first chapter, which was written primarily for designers and people who write specifications to help them write a proper specification and avoid what we call the arbitrary value, which is, say, 5%, just some random number that's a percent of airflow design, because leakage is really not a function of how much air you put into the duct system. It's a function of the pressure, the static pressure that's there, and the what we would call the size of the hole. Okay, I mean, if you were to do leakage in a test specimen, you would create a hole, and from fluid dynamics, fluid mechanics, we know that if we know the size of the hole and certain characteristics of the hole, and we know the pressure differential on either side of that hole, we can calculate, how much air is going to leak. That same principle applies to duct leakage, and so that's why we don't use a percent. Percent is would be better used as a design target, but not necessarily as a pass-fail criteria.
Okay, excellent. So now, I guess let's starting from the designer's standpoint. Ductwork construction. I guess what are the main components that would go into ductwork construction?
Okay, well, the main pieces of information or the components. Basically, duct is some form of tube, and that tube generally comes in one of three shapes. Either it's rectangular, round, or flat oval. And they all have similar components. They're all made up of what we would call joints and seams and or transverse connections. Those are used at the joints. That's how you connect one piece to the next. And then, of course, reinforcement, because you have to reinforce the ductwork so that it does not come apart, or so that it limits the deflection, so that when you apply pressure, it's not swelling up to the point that it's pushing out ceiling tile and things of that nature. And then there are other, I guess we could call them components, but they're not like a physical component. Would be duct sealer, I guess, would be another component. But that makes up the majority. All right. Joints, seams, reinforcement.
Now, and I guess and I guess we'll talk about that when we talk about pressure classes. But so the joints, the different types of joints that you can have for the ductwork construction, what sort of different joints do you have? Well,
for rectangular duct, you're really down to a handful of joints and seams that are used. And I guess while I have the opportunity, I'll say, because I do see it, it's a good opportunity to update your specs. Sometimes we see specifications that limit joints to a certain list, and they're not even the types of joints that are used anymore. For instance, like something called a pocket lock or government lock. Those aren't really used anymore, primarily because of leakage, actually. They tend to be leakier than others. But the main ones that are used now on low-pressure ductwork, and we hate to use that term, by the way, because we have pressure classes, but low-pressure ductwork figure, maybe 3 inches and under, possibly some cases up to 4 inch, but so we'll say 4 inch and under. You can use what are called slips and drives, and they are kind of, as the name implies, they allowed you to assemble rectangular duct by slipping 2 sides together, and then the other 2 sides are driven together as a clamp, and that kind of holds the whole thing together. And there are 2 basic types. They're what we call flat slips and flat drives, and they are, if you just look at them, they're, very flat. They don't have any rigidity to them. They're like almost like the thickness of a ruler, for instance, if you look at them from a cross section. And then we have standing slips and drives, which have various pieces of metal that are shaped in there to actually give it some rigidity. So they would look more like the shape of an L or something of that shape. So you have a leg that sticks up. Those not only join the duct together, but also count as a reinforcement. And then we also have what we call, as a generic term, of what's called a formed-on flange. And they typically go by the trade names of like a TDC or TDF. And these are actual flanges that are formed on the ends of the rectangular duct. And then they go together just like a flanged connection. They usually have a gasket or sealant between them, bolted at the corners, and then they are clipped together, or they can be put together with screws. Those tend to be used on higher pressure or larger ductwork. It's a more rigid connection. Also tends to be able to achieve lower leakage, but again, with proper sealant application and proper application, you can and proper fabrication techniques, you can get most systems either high or low pressure around what we would call a leakage class of 4. But you just want to be cognizant of that in the specification. If you simply say, build the ductwork to 2-inch water gauge and there's really nothing else in the specification, it would not be reasonable to expect that to hit a leakage class of 4. You'd want to definitely specify, and we'll cover this a little later, a seal class A, and I would put in my specification what you expect the pass-fail criteria to be up front, saying, however you fabricate the ductwork, we expect it to achieve a leakage class, say, of 4, which would be a pretty reasonable, a low number and a pretty reasonable number to achieve in most systems. And that covers the primary. Oh, and I would also say you can get what we call slip-on flanges, which are the same concept of a TDC or TDF, but instead of being formed right out of the piece of duct, it's a separate flange that you typically purchase. It's not usually manufactured by the contractor, and you slip it onto the raw edge of the rectangular, screw it to the duct, and then that makes a flange on the end, and you put that together very similarly to the TDC or the TDF. And then, of course, round and oval, they primarily go together in one of 2 ways. Their primary method is what we call a slip coupling, which would be inside the ductwork, unlike piping, which is typically coupled on the outside of the pipe. The ductwork is joined on the inside. That's the primary method for, well, you can use it on all kind of diameters, but my experience has been once you get to, say, around a 3-foot diameter for round, or on oval where you have a flat span that exceeds, maybe 30 inches, it starts to get hard to slip it together. And so then they go to a flange system. And again, those flanges are not, although I have seen some now, they're not typically formed on the duct itself. It's typically something that you add after you fabricate the duct. You add it to the raw edge, again, screw it to the duct, and then in the field you would join the flanges together. And that covers the majority methodology of commercial fabrication. On residential side, you do have like a slip connection for the round ductwork, where one piece basically slips into the next, but that's not typically done or even permitted on commercial application.
Great. Now, I guess the one thing that we talk about when we talk about the duct construction is that it should be assigned a pressure class. What do you expect it to be? So can you talk a little bit about pressure classes?
Sure. The pressure class, and what we're interested here is the static pressure, not the total pressure, for the ductwork, because that's the pressure that actually pushes on the walls of the duct. And when you give a contractor a pressure class, that tells them they would then go to our duct construction standard and fabricate the duct according to the standard, and it would be designed to withstand that static pressure, and that standard is developed around deflection limits. So it's not like the ductwork, if you say build it to 2-inch water gauge and you take it to 2.5, it doesn't go boom, doesn't fall apart. It basically deflects more than the limits that we have assigned in the standard, or at least that would be the expected result. And when it comes to that, we see I know as an engineer, it's common for us to assign safety factors to things. That's just how we do things. But I do see in a lot of cases, ductwork is what I would call over specified when it comes to the construction class. And sometimes the response is, well, if the fan itself is capable of 8 inches of static, and we don't have an 8-inch pressure class, it goes from 6 to 10, you would basically tell the contractor, or at least this is practice sometimes, build the duct to 10-inch water gauge. But the system itself, when it operates, would never see that high of a static pressure. And when you do assign that higher static pressure, you really can really make it a lot more expensive to fabricate the ductwork. A better approach, a more practical approach, in my experience, is figure out what the system is going to actually operate at or very near. Okay, and that's what you want to assign the fabrication or for the ductwork. And if you're concerned about a situation of overpressurization, you should put in some type of pressure relief door. And basically, a pressure relief door is intended to, when the system exceeds a certain pressure level, the door pops open and it allows the system to equalize with the atmosphere and thereby preventing the collapse or burst of the duct. And ductwork is much more likely to actually collapse under negative pressure than it is to burst under positive pressure. But that allows you to build the ductwork to the static pressure that you expect it to be under operating conditions and still cover the what ifs. If somehow the controls, overramp the fan or something, all the VAV boxes close simultaneously or something that would cause the static pressure to drive up. That's a better way to approach it. It's much more cost effective. And what happens in the reality is if you specify those higher pressures, it starts to take options away from the contractor as far as fabrication, which typically means it's going to be more expensive because there are less expensive options. And it's not necessarily justified. There are better ways to approach that.
Now, I guess something that kind of goes along with pressure classes is the seal class. I mean, can you explain that and how that relates to the pressure class?
Sure. The seal class is something that's actually there's three things that I'll mention that are often sometimes misconstrued or confused or mixed together or whatever you want to call it. One is pressure classes, which we already covered, which is how you fabricate the duct based on the static pressure we expect it to operate at or below. The next question you asked me was, what is a seal class? Okay, seal class is simply a class, and there's three of them, A, B, or C. Although quite honestly, practically now there's only one, which is seal class A, and we'll cover that here in a minute. That tells the fabricator, the contractor, where sealant needs to be applied. Okay, and our standard, the duct construction standard, has minimum levels of seal class based on pressure class as just a minimum level. So, for instance, if you're fabricating low pressure ductwork, it's typically low pressure, again, maybe 1 inch, 2 inch. It's required to do what is called a seal class C, which is just transverse connections. And then at 3-inch water gauge, we would expect you to do a seal class B, which is transverse connections and longitudinal seams. Spiral seams, by the way, are always exempt from sealant. It's a pretty tight seam, and again, it does have some leakage, but it's usually pretty minimal and not practical to seal that. But that would be a seal class B. And then a seal class A, of course, is joints and seams plus any duct wall I say applicable penetrations because there are things that penetrate a duct wall that need to be able to move, sometimes like a volume damper control arm. We've seen, and this is one of the issues that comes up when somebody specifies a pass-fail criteria on a leakage test that's really too low. Even when everything is properly installed, they cannot pass. So what happens is a lot of times the contractor will be forced to go in and seal up things like control arms on volume dampers and whatnot to pass the test. But obviously, if you're familiar with duct sealant, it's like an adhesive. It's not something that typically stays movable and flexible. So you're basically gluing that control arm in whatever position it's at, and then the balancer comes in and can't balance. They either have to break that seal, or quite sometimes they actually have to reinstall a new volume damper because the sealant is that aggressive of an adhesive that there's no way to fix it. I mean, you have to break it loose. So that comes into doing a proper specification. But again, aside from things that are supposed to move, generally Seal Class A means seal it. The only other issue where we have a slight definition difference between a couple of organizations is the screws. We would say for Seal Class A, it is not mandatory to seal every single screw that penetrates the side of a duct. And the reason we go that route is because especially if you have exposed duct work and you say, I want to seal Class A, you should not, for aesthetics, you don't necessarily want to seal all that stuff up. But that doesn't mean you're forbidden from doing it. So if you have to seal the screws for whatever reason in order to achieve a reasonable pass-fail criteria, then by all means, you seal it. But we don't want to make that mandatory across the board. So that's one of our differences, I guess, between I've seen some people define Seal Class A to include all screws no matter what, and we don't really feel it does add some leakage. Most of the testing we've seen does not show it's a significant amount, but a lot of that has to do with proper installation of the screw, etc. And so we leave it in the address it as needed. In other words, if you can't pass and you find that sealing the screws allows you to pass the test, then go ahead and seal the screws. But we don't want to make it a mandate because there are cases where you don't want to see that sealant applied.
Okay. Now, in getting to, I'm just kind of thinking of some of the ductwork that I've seen and the construction processes. Now, I've seen, day after day, all the joints between the pieces of ductwork, the mastic being put on it and the sealant being put on it. But, I'm trying to think, the longitudinal seams, the one that goes along the length of the ductwork, I typically haven't seen that same sort of sealant used along that seam. I mean, is there something, because usually those pieces come to the site, fully constructed. So is there something in the process where, when they're constructed in, I guess in their shop, that they actually apply the sealant there so it looks different?
Yeah. For rectangular duct, the longitudinal seam, and again, for round duct, if you're using spiral seam, there's no sealant. But for rectangular duct, in the longitudinal seam, which is typically found in the corners, most of the time that is fabricated, if it's just a regular piece of duct, in a machine called a coil line. And part of that process is to inject a sealant in that pocket, where those two pieces go together. So it is sealed. It's typically sealed at the fabrication. And the reason they use a different kind of sealant is in some cases, Matt, a lot of times they do send it pre-assembled, but if they do assemble it on site, they want that sealant to stay soft until the two pieces are joined together. So they actually use a different kind of sealant. Now, that doesn't forbid you from using a brush-on sealant, but it is typically injected into the pocket of either that's called a Pittsburgh seam or a snap lock seam. It's typically injected. Now on round duct, it is typically not, but there are products out there. I can think of two offhand. One is done very similarly to the rectangular, where it's a product that's put in there that stays soft until you put the two pieces together and it creates a seal. And then I've seen another product that's almost like a dry, very soft foam that creates that seal. And typically on the round products, because those are not manufactured by the contractor, that's something that the manufacturer themselves provide and it's purchased, they will typically somehow mark that product with a name or a sticker or something to tell either the inspector or engineer or anybody who's concerned that that's a product that has a seal already applied to it. Now, rectangular duct, though, which is typically fabricated by the contractor, you have to look, you have to know, and you can usually tell. You can, if you look at a piece of unassembled ductwork, you'll see the sealant in there. And actually, if you're really that interested, you can actually sometimes from the end of the duct, if it's the ductwork's assembled but not installed, you can also see that sealant has been applied.
Now, I guess looking at these different types of applications, like pressure class and the sealant itself. How do you know that? I mean, obviously you have to be a little bit familiar if you're looking at the pressure class, the duct construction, what to look for as far as the reinforcing and things like that. But as far as can you look at a piece of duct and be able to tell this is a pressure class 2? Because I typically don't see it marked on ductwork. I don't know if your experience or the standard is different, but that's something that how do you evaluate ductwork when you see it?
Well, there are some general things that you can look at again to give you an idea of what range you're in. For instance, if I see flat slips and drives, okay, that ductwork better typically be fabricated to 2-inch water gauge and below. If I see flat slips and drives on 4-inch or 6-inch water gauge, I'm going to question it. Now, there are some applications where you can do that, but you're limited in size. Okay, so again, if it's large or high pressure, I better not see flat slips and drives kind of a approach. As far as things like gauge, it's pretty difficult to eyeball gauge. If you work with sheet metal, believe it or not, those guys can tell by picking up a piece what it is because they work with it day in and day out. But from an inspector standpoint or an engineer standpoint, it's a little bit tough. But most ductwork that I've seen actually has a sticker on it because it's part of an assembly process, and it usually tells you what gauge needs to be used. And I can tell you from working at a duct manufacturing place, that was always treated as a minimum. Sometimes, you don't have enough of that lighter gauge. It's certainly acceptable to use a heavier gauge. You just don't want to use a lighter gauge. But our standard, one of the good and kind of bad things about the standard, if you will, is that there isn't one way to build ductwork. If you gave me a size and a pressure, I can probably give you at least 5 different ways, at least 4 different ways to build that ductwork and still be compliant with the standard, whether you use internal reinforcement or external reinforcement, and a number of different connections and several different gauges depending upon what reinforcement spacing you're using. So it's pretty difficult for someone, if you don't have that experience, to just look at a piece of ductwork and tell. But there are certain things, like I said, if you're using flat slips and drives, you want to make sure that that's typically used on what we would use the term low pressure stuff. And that's kind of a start. And that's usually the kinds of things that get caught, quite honestly. It's not usually the gauge unless there's an issue after the fact. Mm-hmm. That's usually when those things kind of come up. But most contractors, because we deal with these questions all the time, they usually get the gauge right. If it's anything, they sometimes make mistakes on the proper reinforcement. Now, something that can be done, I guess, and we have a number of people that have taken advantage of this, but not everyone. We actually have a separate group called the Testing and Research Institute at SMACNA, and contractors can submit their shop standards to SMACNA to be reviewed, and they will get a review, and if there's errors, then we'll tell you, hey, the gauge is too light here, or it's not the proper reinforcement. We'll even tell you if you're overbuilding the ductwork. Of course, that's still compliant, so you can continue to do that. That's not against the rules, but you don't need to, in which case you can save some money and decrease your bid pricing and offer a more economical option to the engineer and owner. But you can do that, and a number of contractors have done that, and so an engineer can quickly go to an engineer and say, look, here's my shop standards. It's been reviewed. And we found that, the majority of the time, ductwork is built to the shop standard. Of course, there's always a case where, somebody made a mistake along the way, and that does happen, but that's pretty rare. And the reality is, Matt, we don't have daily occurrences of ductwork either exploding or imploding. So the industry at large, basically, I guess you can say, gets it because it's not a daily issue.
Mm-hmm.
I mean,
So I guess what's the best way for engineers to communicate this? Is it going to be in specifications? Is it going to be on drawings? Should you do one or the other? Should you do both? What's your feelings?
Well, of course, the default answer is the more places you put it, the better. But it is good to include information on drawings because let's just face it, from a practical standpoint. Usually by the time somebody gets the project and puts together a bid, they're focusing on the drawings and doing a takeoff. I used to do that when I worked at McGill. It's kind of unfortunate when, and a lot of folks use them, and I understand why, but you have what are called canned specs, they use specs from job to job. I've certainly run across cases where someone will have in their specs something about double wall duct, but there's no double wall duct on the drawing, and that always leads to the question: did I miss something, or is it not there, or having it in both places, I guess, never hurts. Certainly, the pressure class, it wouldn't be hard to mark on a drawing what the pressure class is. You don't have to do it on every single piece. You can do something typically like on a VAV system. You can even note, ductwork upstream of a VAV system shall be constructed to whatever 4-inch water gauge. Ductwork downstream of a VAV box can be constructed to 2-inch water gauge. I would say it only makes sense now to basically flat spec seal class A on almost all ductwork. It doesn't really add that much cost. In fact, most contractors will tell you it's certainly worth the effort to put the sealant on duct, even on the low pressure side, just because it does reduce the leakage. And that's really what's becoming the norm. A lot of contractors do it anyways, whether it's specified or not. But even if they didn't, you're seeing, for instance, ASHRAE 90.1 is starting to require seal class A. Even the base mechanical codes are migrating. They're not quite there yet, but they're migrating to a seal class A. And that's something that SMACNA, is in support of. It certainly makes sense to seal the ductwork, high and low pressure, if you will.
Okay.
But the other thing to really specify, this is the part that is often missed, is what the leakage class is, and we kind of didn't talk about that yet. We talked about seal class and pressure class, but the more important number, if you're going to do any kind of performance testing, is the leakage class, and that is what you expect that ductwork to pass or fail at when it's properly fabricated. Of course, you want to pick a number that makes sense. Our standard, basically, we provide numbers based on research. We've built ductwork, we've sealed it to certain seal classes, and then we've tested it, and we have a range of seal classes. But if you want to be on the aggressive side, or you want to keep things tight but still be reasonable, I would say assigning what we call a leakage class of 4, which basically mathematically translates into 4 CFM for every 100 square feet of duct surface area tested at 1-inch water gauge. Okay, and there's a relationship there. So if you test it at a higher pressure, you can expect more leakage than 4 CFM for every 100 square feet. It's not a linear relationship. It's basically to the power of 0.65.
Now,
but that's the way to do it.
Now, how do you go about testing the ductwork? I mean, what's the process there?
Typically, testing the ductwork, and there's a couple of slightly different approaches, but the basic concept is you cap off a section of duct, okay, and then you hook a device up to it, which is generally called a leakage tester, and it consists of a fan, something called basically a flow meter, and they're usually what's called an orifice tube, although I've seen ones that use venturi as well. Basically, that just measures the amount of air. And then you hook that up to your duct section that's been blanked off or capped off, and you start the machine at a low speed or with the inlet damper completely closed. You turn the machine on, and then you slowly open the damper to pressurize the system to whatever the test pressure is. Okay, and the machine has 2 pressure caps one that measures the pressure or the static pressure in the duct, and the other measures the static pressure across an orifice plate. Okay, and if I know the difference of pressure between the orifice plate, and I know some characteristics of the orifice plate, I'm measuring how much air is going through. So really what we're measuring is how much air we're putting into that system, but of course, conservation of mass, whatever goes in must come out, so you're also measuring what's coming out. So you assign a certain test pressure, hook the machine up, and bring the system up to the test pressure, and you're measuring at that point what the flow of air is to maintain that pressure. And that flow is basically what we would call the leakage. Now, to touch on that a little bit, because we see this as well, just like engineers were typically, I don't want to say typically, but often over-specify the construction of ductwork, they'll also ask for the system to be tested at a higher pressure than what the duct is constructed to, and that is a big no-no for two reasons. Number one, there's no real reason, it's not practical to do that, because if you want to measure the leakage of the system, it doesn't make any sense to measure the leakage at some higher pressure anyways. The numbers you're going to get don't make any sense relative to the system. And number two, the more important reason is if your goal is to actually turn over a well-constructed duct system that is relatively tight, over-pressurizing it doesn't do a good job. It actually can over-deflect the ductwork. It can cause sealant to come out and gaskets to blow out. So you never want to do that. In fact, we're migrating to what we would call a system test, to where you can incorporate pieces of equipment and other things in the test, because we would say right now you should isolate the ductwork and test the ductwork. But one of the, and this isn't a finished standard, so this is kind of, until it's final, it's not final, obviously. But what we're looking at or experimenting with is doing all tests at, say, 1-inch water gauge. Because we have shown, and we can see through research, that if I know the leakage at 1-inch water gauge, I can very accurately predict what it is at 2, 3, 4, 10 inches of static. So I don't need to do those high pressure tests in order to tell whether or not something is relatively tight. The purpose is not to do a stress test. It's really to do a leakage test. And that's one of the big issues that we see all the time. Test at 2 times the pressure or 1.5 times. You want to avoid that. You never want to test above whatever the construction class of the ductwork is for leakage. You never want to do that.
Now, I mean, is for say a different a system, are you going to test all the ductwork, all the mains? Are you gonna just pick a couple of different locations just to make sure that the construction is consistent, or what? What's the thought on that?
Well, that's a very good question and an area of a lot of debate. Depends on who you ask. But I think the majority of people that I talk with, and certainly my opinion on it, is you can certainly do a sampling. It is not necessary to do 100% testing. And of course, the argument to that is, well, how are you sure if you don't do 100% testing? Well, the reality is very few industries do 100% testing. It's not necessary because there is an expense associated with doing that. So you try to find a point of testing enough of the ductwork to show that good practices and proper installation are being done, but without just adding significant cost. And what we're actually starting to promote or advocate for in the codes is what we would call as an example, a 20-40-100, meaning you would test 20% of the ductwork based on surface area. If you pass that 20%, you're done. You've demonstrated that you've done a good job. If you fail that 20%, of course you need to fix it to bring it into compliance. But by fixing it, you'll learn what caused the leakage, what caused the failure. And then you have to test another 20%. Okay. If that second 20% passes, the general thought is you found an isolated case, and so you passed on the second test, so you don't have to do any further testing because you happen to find the area where what caused the leakage. But if you fail that second test, there's a good chance you have something that we would refer to as a systemic problem, or something in your fabrication or installation process that was not done correctly. For instance, one scenario might be only applying sealant on the bottom and sides of the duct because nobody can see the top. But of course, if you test it, you'll find that. Well, if you fail 2 sections, there's a good chance that you've carried that practice on, and after failing the second attempt, you would then have to do 100% testing. And the reason we advocate that versus doing automatic 100% off the bat is, as an owner of a building, okay, if you specify 100% testing, then you're paying for that up front. And the reality is, Matt, that there is no real benefit to testing ductwork, okay, unless somebody fails. If you fail and find a problem, then you fix it. There, you now have a benefit. But if you simply pass the test, you're certainly confirming what was done. I guess there's some value to that, but you're not really saving any money in the long run. So that's why we advocate a stepped approach to doing the test. And by only specifying 20% up front, but then putting in conditions that if you fail, you have to test another all the way up to 100%, that then puts the a responsibility on the contractor. Meaning, if you don't pass that first test, I mean, that's what was included in your bid, you're now responsible for paying for the test, second test, and maybe a third test, because you don't include that in your bid. You only include, a good contractor would only include enough to do the 20% testing, because that's what's mandatory. The rest is only if I didn't do a good job. Now, the flip side to that is you, of course, have to assign a pass-fail criteria that makes sense. You can't assign a pass-fail criteria that's artificially low or doesn't make sense. So you want to do your research before you just assign some leakage class, because what you want to prevent is somebody who actually does things correctly from being penalized. And as far as high pressure and low pressure, that's another argument. Of course, as I said earlier, leakage really is a function of the pressure. So, of course, high pressure areas where the ductwork operates at a higher pressure create a bigger potential for leakage, assuming that the holes are the same size. Now, some people argue, well, you should test all the ductwork because you can still get a lot of leakage on the low pressure side. Well, that's true and false, and let me explain if I can. It is true that if I tested every piece of duct at the same static pressure, and especially if I didn't seal the low pressure side, I would expect the low pressure duct to leak more. Okay? But part of the true reality, the bigger picture, is that low pressure duct also operates at a much lower pressure. It rarely even hits a half-inch of static downstream of a VAV box. So when you look at the results of running at such a low pressure, even what would be conceived of as a large hole, I mean, you can literally drill a hole in the side of the ductwork. When you test it at that low pressure, you'll see that it doesn't make a huge difference. So does that mean you should never test low pressure ductwork? Not necessarily, but it certainly, from a practical standpoint, makes sense to not test all of it. In other words, if I was to focus my testing, I would focus more on the high pressure side. Might I specify testing a little bit of low pressure just to for my own satisfaction? Sure, but would I keep that relatively small? Yes, because that's not really where your big issues typically lie. But if you do a test and you see a failure, again, using that stepped approach of 20, 40, 100, you now have a method to go in and say, okay, well, we did a low pressure test. You failed that low pressure test, so I want you to test some more low pressure duct. Oh, okay, you only failed that one. You tested the next couple sections and you passed. Okay, good. It also might bring to light some issue. And that's why I advocate doing some testing early. And even, the contractor should want to do the testing early, but even as an engineer, someone who's going to go out and enforce the spec, it's good to do some duct testing early in the project. And the reason is, if the contractor is failing the leakage tests, they can probably find out why they're failing the leakage test and fix it before they complete the project. If you're towards the tail end of the project and you start doing leakage testing and you find that there's some issue, for instance, let's go back to the discussion on the screws. Oh, I should have sealed the screws because I can't pass the test without sealing the screws. Well, now somebody's got to go back and start sealing a bunch of screws, which is very time-consuming. And in some cases, depending upon the length of the project, ductwork may not be accessible anymore. It might be behind drywall or something else, and then it becomes pretty impractical to go back and seal that. So doing some testing early, letting the contractor know, where the bar is to be set. And of course, this isn't the sole burden of the engineer. I mean, the contractor should want to do this as well. But as the person who enforces the spec, the engineer should go out early on in the project, do a couple of leakage tests, and kind of let the contractor know, this is where I expect you to be, and we're going to do some more testing as the project goes on, but I want to set the bar. I want you to know where the bar is so you can hit it and not create some problem down the road that we have to go back and deal with.
Now, how would you, differentiation between supply ductwork, return ductwork, exhaust ductwork? any sense, obviously supply, high pressure side we've talked about as being, a very critical area. Return, is there any sense in testing return, or what about exhaust? I would think that maybe more exhaust than return, or how do you see it?
Well, I mean, no leakage is good. I mean, all leakage in some form or another does impact the system in a negative way. So I think it's important to do some testing of any ductwork. Mainly because, again, you want to show that especially if you're using different pressure classes and different techniques, you want to make sure that whatever the technique that they're using and the fabrication that they're using makes sense. But yeah, you can ductwork that is probably highest on the priority list would be ductwork that's actually either on the supply or the return that is located outside the building envelope. So if it's a return and it happens to be on a rooftop or something of that nature, or supply and it happens to be on a rooftop or outside the building envelope, those are areas because that is totally outside of conditioned space. So any air that leaks out or leaks into that system is, unconditioned air. Whereas, like you were saying, or alluding to, that if it's leakage that's in a conditioned area, yeah, it might be leakage, but it's not as bad, and that's true. And then certainly on the exhaust side, yeah, that makes sense as well, is to do a little bit of testing on that. And that's why you'll see in ASHRAE 90.1 2010, and we were involved in implementing the change, you'll see that you test 25% of the ductwork, anything that operates above 3 inches is static, and all ductwork located outside the building envelope. That is what's required in 90.1 to be tested. So that's kind of where I would say are your main areas of focus. But doing a little bit of testing, I don't think it's as big a deal to say, well, am I going to test low pressure or high pressure? I think there's a justification to test high pressure, low pressure, supply, return, and exhaust. I think it just makes sense to do it practically and say, let's test a portion, or let's, if we have 4 exhaust systems, let's test one, or a portion of each, or however you decide to do it. But, that's where the practicality comes in. And part of that is knowing the building, too, as a designer. Certainly, if it's exposed supply ductwork like you see in some restaurant chains, or I actually happen to be part of being an engineer, every store I go in, I look up and see what's going on. I was in a bike store yesterday and noticed, again, all exposed ductwork. Is that leakage detrimental? No. Is it still not good? Yes, because it's not coming out of the diffuser, which was part of the design process, but that is not going to impact the system the same as ductwork that's located, for instance, on a rooftop. But no leakage is really good, but certainly has different impacts. So one other thing while we're talking about that, sure. Actually, because there's a misconception that if it's a return system or an exhaust system, then I have to test it at negative pressure. And we've actually done tests for positive and negative, and what we find is that if you test all duct at positive pressure, that's fine because the actual results that you get are within the margin of error of the test anyways. So it isn't necessary to test an exhaust system at negative pressure or a return system at negative. You can actually pump it up positive, and that actually reduces the expense in setting up the test. And so that's a practical decision. In other words, go ahead and test it under positive pressure, still assign a leakage class, and you're fine. That isn't necessarily true of equipment, and that's kind of a whole separate discussion. But equipment, because it typically has doors and flaps, it actually leaks very differently, whether it's under positive pressure or negative pressure. And again, that's why we're working on a test to address those things. But for right now, as far as duct is concerned, positive pressure testing is fine, even on negative pressure systems. And it actually says that in our standard and in 90.1 2010, it specifically addresses that.
So I guess what other changes are coming up in the duct leakage environment? Especially when with other codes and guidelines and different criteria, whether it be green criteria or the IGCC or I guess. What sort of things are coming up? Obviously you've mentioned the going to a straight seal class A. What other things are they looking at?
Well, like I said earlier, right now, basically 25% of what I'll call high pressure or anything that's above 3-inch static is required to be tested. That's consistent with the International Green Construction Code, the International Energy Conservation Code, and ASHRAE 90.1. That's kind of where they're at. And it's for ductwork, okay? It doesn't include equipment. Where we're migrating towards, and we're actually working on a standard right now that ASHRAE has decided to co-sponsor as well, for the system, because we've seen from the design community through their specifications that they want a system test. Okay, and that kind of goes into the realm of commissioning. It's really no longer, we'll say, acceptable to simply test one portion or one component of a system, or each component of a system, and assume that if each component passes, that the whole system operates. But we need a way to evaluate the system. We can still do that in sections or by testing a portion of it, but we need to address the other components. So we're working on a system test. It would be a way to, same basic process. You hook up the tester, you cap off a certain portion of the system, except it could now include a VAV box or fire dampers and other things that are typically found in the ductwork, and then a way to test that. And right now what it looks like we're doing is you're going to get, you would add that up. You would say, okay, I know the VAV box is going to leak, 25 CFM at 1 inch of static. I have a method from SMACNA to do the ductwork, so I know the square footage, and I calculate the leakage for that. I know what the volume damper is going to leak. So when I hook this thing up and test, that's the number I expect to be at or below. And if I'm not, we have an issue. And that's kind of where we're going. We're trying to negate the concept of just this arbitrary percent. I realize that's easy to do and it's done in the industry, but unfortunately, leakage is very system dependent. Of course, a section of just ductwork, I would expect to leak a lot less than a section of ductwork that includes a fire damper and possibly a VAV box. So there's reasons to say it makes sense to do it in this process of actually figuring out what the acceptable leakage is, and it's not just an arbitrary percent. But where we do feel the percent makes sense is from the design side. So when you're designing the system, of course, and if you want to keep your overall leakage below 5% or some number, you can certainly go through and tally up the leakage. And if you're over this 5% number, you can go back and look and say, well, maybe we specify a tighter VAV box, or we find a way to we route the ductwork to reduce the number of fire dampers or something along those lines to reduce the anticipated leakage. But that's where the percent comes in. But we're working on that standard. We hope to get that involved. You're also going to see right now most of the standards don't require testing, again, what we call low-pressure ductwork. You're going to start to see standards come out and codes come out that are going to require the testing of low-pressure ductwork. Again, we're advocating do it in a stepped approach. Don't mandate 100% testing. That can add a significant amount of cost to a project. And again, there's no benefit to that. Testing the ductwork does not reduce the leakage. Sealing it does. So specify seal class A, test a portion of it to make sure that and test a little bit early, test a little bit late to make sure everybody's doing what they're supposed to do, and that makes sense. And then have a clause in there that says, well, if you fail your test, we want to do more testing, and of course, all the way up to 100%, so that it's justified. We feel that's kind of the overall best way to approach it, and so that's where we think you're going to see codes, standards, et cetera, start migrating towards. And eventually, this is theoretical, really theoretical at this point, is after we have enough data to support, we know certain products work and certain procedures, we might even get to a point where, if the ductwork and equipment is installed by somebody with a certain certification and the products have been through some kind of test that's a certified test, that you can really reduce the amount of testing, because we know that the person installing it has been trained and that they've been shown to be consistent in installations. So there's some benefit to bringing that certification to the table. I think we're a little ways off before we get to that point. But it's certainly something that may come up in the future. And again, the goal here is to deliver a system that performs well, but try and keep the costs reasonable. We don't want to just add cost for the sake of adding cost. That really doesn't benefit any industry.
Great.
And lastly, I guess this isn't really new, but it's relatively new, but it's already out. Is in an effort to try and get folks away from using the arbitrary percent method, we have a duct leakage app that's available, and you can go to our website. Is the easiest way to. You can actually use it online. You don't even need a smartphone. It's www.smacna.org/DALT for duct air leakage test, and you can you just punch in the size of the duct, the test pressure, how many feet, and it'll tell you the allowable leakage, and it allows you to add sections together, because typically you don't test one section of one size of duct. You might have some rectangular, some round, all in that test, and it'll allow you to generate a little report you can email to yourself or anyone for that matter, and you can see what the pass-fail criteria is. And it uses a leakage class, and it will populate with a suggested leakage class based on the information you put in there, but you can certainly go in and change that. You can change it to whatever leakage class you want, just to see, how it applies and affects.
Great. Now, I guess is it, to learn more about duct leakage and things like that, where can people go to get more information?
Okay. We have a couple of white papers on our website. Again, SMACNA.org. Go to the technical services link, and from there you'll see white papers and bulletins. And there's information just in general about the industry there. Certainly information on duct leakage as well. You can also go to the ASHRAE TC 5.2 website. We recently had 4 speakers, and we did a presentation at this year's winter meeting, which I think was Chicago, right? We did a presentation out there, and we've contacted all of those folks. One is from me, one is from Craig Ray, one is from Dr. Mark Madera, and one is from Galen Richardson, I believe. And we all have maybe slightly different points of view, but all those presentations, I believe, are up on that website. You can download those PowerPoints and kind of go through them and see, the impacts and procedures and suggestions and thoughts and anything related to that. But those are some good sources for information.
Great. Any last words for me, Mark?
No, just I'll reiterate. I guess yes. I'll reiterate a couple of things. Big no. Never, ever, ever assign a test pressure that is beyond the construction class of the duct. It makes sense to just put in your spec, even though it's starting to become mandatory anyways, seal Class A for all duct work. And it certainly makes sense from the laws of physics to assign the pass-fail criteria based on a leakage class, not an arbitrary percent. If you do those 3 things, and especially if the leakage class is something that you can justify, not, again, just some number that you pick out of the sky. Like I said, leakage class 4 is a pretty good number to address all types of ductwork. You can get a little lower on spiral round, et cetera. But if you do something like that, it's a pretty hard argument to come back and say, you're asking for something that's unrealistic. If you ask for those things, you're in line with what the green codes and those aggressive, we'll call them aggressive reach codes, are asking for, and it's still consistent with something that can be expected of from the contractor. You're not asking for something that's out of this world, so to speak.
Great.
You do those things, and I think that you take away arguments, I guess, if it's an area that you fight as a engineer or a building owner. There's really no argument left.
All righty. Well, I appreciate your time, Mark, and appreciate a lot of good information, and hopefully we can get this information out to designers, out to contractors, and help them kind of understand better exactly, duct leakage and get that common foothold, so they're all talking the same language. So I really appreciate you being on the show.
No, my pleasure. Anytime. Thanks, Matt.
All right, and we're back. Thanks to Mark Terzigni for talking a little bit about duct leakage. Those are some of the things that are really kind of the meat and potatoes, the verification that things are going right, at least in my mind. And it's always nice to be able to kind of get some of that information from SMACNA. They have great manuals online. You can order those through their bookstore. I'll try to post some of the links that Mark was talking about on the show notes, so you don't have to write them down or scribble them down. So other than that, remember, I think that we kind of ran a little bit long there, but that's okay because it was good information. So I guess if you want, if you have any comments about that episode, too long, too short, things like that, you can always contact me, Matt, at buildingx.co, or you can follow me on LinkedIn or Twitter at buildingx, if that's your thing, if you're one of those people. So if you, I appreciate each and every one of you listening. We'll come back again and do it again next week. So until next time, remember, know what you build and share what you know.